So I spent a couple of hours porting all the code over into this new format, and I want to spare you all this editing work. So in the final code, that is a little bit incomplete still, we have a grid, we run a function called main. Main then runs a path planner, a star, smooths it, and then runs a controller, as in run. And in the controller, I even implemented for you our particle filter that you're familiar with. There's nothing new here. You're running the exact same code from class that you programmed yourself. And then I go through a loop where I compute a cross-tag error, apply my only PD controller, there's no I term here, and I run my particle filter as before to estimate where the robot is. What I would like you to do is to implement the cross-tag error function. And I want you to use as an input the estimate, not the actual robot position, but the best estimate, which we can get by running filter.getPosition. Now here is the difficulty. And I can tell you confidently, it took me more than an hour to solve this problem myself, just for this class. Our path now is a sequence of linear pieces. When a robot drives along, it has a certain cross-track error. But as the robot state projects beyond the end of a line segment, as is happening here, we have to change the corresponding line segments to be the next one. So in addition to calculating the signed error relative to an arbitrary line segment, not just the y-axis, we also have to detect when the robot steps beyond the end of a line segment and switch over to the next one. Now suppose this is our line segment, and the path is given by the coordinates of the beginning point, P1, and the end point, P2, both of which are xy coordinates, which you get straight in the path. Suppose our robot's position is something like this, where it has its own xy estimate that comes out of the particle filter in your case, and it has its own orientation, theta. Then both the cross-tag error, as well as how far it's progressed along the line segment, call this u, can be calculated using a dot product. Specifically, let's call this vector over here delta x and delta y, as defined in x2 minus x1 and y2 minus y1, this vector over here. And let's call this vector over here rx, which is x minus x1, and ry. Then u, the ratio of how far we've progressed along the segment, is given by the dot product rx times delta x plus ry times delta y divided over the sum of squares delta x times delta x plus delta y times delta y. Why? Well, this normalizes the vector length to 1, and this is the dot product of this vector over here and the green vector, which happens to define the distance. So if this is larger than 1, we know we've left the segment. It's time to move on to the next one. Finally, the cross-track error, the red one over here, is given by a similar but not identical dot product of ry times delta x. Notice we're now multiplying a y with an x, minus, instead of plus, rx times delta y, with the exact same normalizer as down here. So you can see the normalizer over here. So what I want you to implement is this piece of math over here. When you run your controller, you will find that I set up for you a variable called index. That's the index into your path. When u exceeds 1, we should increment this index. Make sure it never goes beyond what's legal in path length. And the cross-tag error should be computed relative to the current index, and is of course a signed error using the exact same dot product I've shown you. The last thing I want to tell you is what the path is, and I want you to use the following path. The path is called sPath. It's given, the run function is one of the parameters over here. You can see this up here. So sPath index is the indexed element of this path, and 0 stands for x and 1 stands for y. So please fill in the missing code over here. And I should tell you, when you run our controller with the missing code included, you get actually a valid, nice path that mostly doesn't collide. Occasionally does because of randomness in the system, but it should be mostly collision free. And for this example, require about 130 or so robot steps. And just so that you see a typical answer, here is a random run, which means and you read this as follows. True means the robot actually found the goal. 0 means 0 collisions. And it took 137 steps. Let me run it again. And here's another outcome. Robot didn't collide. It reached the goal in 145 steps. I should warn you, sometimes I do get collisions here. And it's because our obstacle circuits are relatively large. The noise in the system makes it hard to navigate. But most of the time, you should be able to get to the goal without difficulties if you implement this piece of code correctly. And just to warn you, it took me quite a while to work this out.